Momentum of an object is its mass times velocity. It can be used along with the law of conservation of momentum to explain and calculate what happens during a collision or during an explosion like this. In this video, we're going to use this law to explain and do some calculations for explosion type of questions. Example number 1. A man fires a gun without securely holding onto it. The bullet leaves the gun at 820 meters per second. The gun recoils backwards out of his hand. The mass of the gun and the mass of the bullet are given. We need to explain why the gun is recoiling. So recoiling is when the gun moves backwards when it's fired. Why does this happen? Let's use the law of conservation of momentum to explain this. So first of all, let's start with the total momentum before. It's zero because nothing is moving at the beginning. But once the bullet gets fired out like this, is going to have a total is going to have momentum going towards right. Have the total still needs to add up to 0 meters per second. So how is this possible? How can the bullet have some momentum towards right? So we can say the bullet has a positive momentum and the gun has an equal but negative momentum. So this way that they add up to 0. Okay, so this is why the gun is going to recoil, and if he's holding onto it, he's also going to get pushed backwards. So let's summarize this. The total momentum before an explosion is 0. Total momentum after an explosion also needs to add up to 0 according to the law of conservation of momentum. If the bullet is going to gain amount of momentum towards the right, so let's say a positive momentum, then the gun must gain an equal but negative momentum towards the left. Okay, so that when you add the positive and the negative momentum, it adds up to 0. Part B of the same question, calculate the recoil speed of the gun. So let's label all the numbers that we have. We've got the mass of the gun, we've got the mass of the bullet, we've got the speed of the bullet. We know that we're trying to find the recoil speed of the gun. Let's break this question down into before and after. We know the total momentum before is 0, total momentum afterwards also needs to equal 0. So let's calculate the momentum of the bullet first, because we've got the mass of the bullet and the velocity of the bullet. So let's multiply those together and we get the momentum for the bullet, and that's positive because that's going towards the right, and we're going to say that's positive. So what can we add to this to give us a total momentum of 0? Well, we need to add negative 32.8. That's going to go to the gun. The gun's going to get equal amount of momentum but in the negative direction. So we know the mass of the gun is 3.5. We don't know its speed, but its velocity. We know that if we multiply the 3.5 by the velocity, it should equal minus 32.8. So if we rearrange this by dividing both sides by 3.5, we get the velocity of the gun is minus 9.4, which makes sense because it's going towards the left, which the negative shows that it's going in the opposite direction to the bullet. Also, the velocity of the gun is lower than the velocity of the bullet, and that's because the mass of the gun is a lot bigger, so it can have the same size momentum without having to go as fast. Example 2, we've got two ice skaters. They're standing at rest in the middle of an ice rink. Person A has mass 50 kilograms and the person B has mass of 65 kilograms. Person A pushes off person B and heads to the left at 4.2 meters per second. Explain the motion of person B. Support your answer with some calculations. So first of all, we're standing at rest in the center of the ice ring. So the total momentum at the beginning is equal to 0, and actually the total momentum afterward also needs to equal 0. They're going to push off each other, so let's label all the numbers and let's start with the calculations. Okay, so we know we're trying to find the velocity of person B and what's going to happen to person B is what we are looking for. So before and after, total momentum before is 0, total momentum after needs to equal 0 as well. Let's calculate the momentum of the person we do know. We know person A's momentum, so it's 50 times 4.2. That's 210 as positive. Let's just say it's positive even though it's towards the left. We know that the other person must get equal amount but negative. We don't know the velocity of that person, but we know the mass is 65 times some unknown velocity v. Let's rearrange this, divide both sides by 65, and that gives us a momentum, a velocity for the person B of minus 3.2 meters per second, showing that they're going in the opposite direction to person A. Okay, now we've done the mass, let's explain it using words. Okay, so total momentum before equals 0, so total momentum after it also needs to equal 0. That's the law of conservation of momentum in a closed system. And so if a person A gains momentum in one direction, person B must gain the same momentum but in the opposite direction. It needs to be the same momentum but negative, basically, so that when you add them up, it needs to equal 0. However, there's a slight difference between these two. They have different mass. Notice how person B has a heavier mass, so that means that even they won't have to go as fast. Their velocity will be lower, but they'll still have the same size momentum.